Okay, now let's take a look at how we're going to actually test a hypothesis. Turns out there are two ways we can actually test a hypothesis. Okay, the first of the two approaches, is called the critical value approach. And the other approach, the second approach we'll look at in the next video, it's called the p-value approach. So what is the critical value here? Critical value is called critical because it actually separates two regions from us, rejection from non-rejection region. But the reason it's called critical because it's the value that we use as our criterion as to whether to reject or not reject the null hypothesis. Remember I mentioned, let's say we claim the average rent of a one-bedroom apartment in San Diego is $1,500. And then we're going to get a sample of size whatever, and our sample shows the average is $1,700. So the question that come up is this: well, is the difference of $200 substantial? Is it really different in the population, or is it the difference is $200 because I'm sampling? Could be sampling error. So the critical value again is the value would be the cutoff for us. So for example, I'm going to say, well, if it's up to $1,800, we're okay. We're going to say the mean could be $1,500. But if I see the average rent in my sample greater than $1,800, then we're going to cast a shadow of a doubt on the null. So that's what the critical value does. In that sense, it's critical. It's the guideline, the criterion we use for rejection or non-rejection. Okay? Remember, that's our cutoff point. So, going down further, how do we determine this critical value? By the way, the critical value directly depends on the size of our test, the probability of a type 1 error. Okay? And what we do with critical value is that difference between the sample mean and population mean. We express that distance in terms of units of a standard deviation. So for example, I'm going to say, well, my sample data is 2 deviation above, or over 3 deviation above, 3 deviation below. So most likely I'm going to reject a null because I have seen an unlikely event. If I see something over 3 standard deviation, that's very unlikely, and I'm going to reject a null. Okay, so that's what the distance is measured in terms of units of a standard deviation between the sample mean and population mean. Okay, now here I have an example. Let's take a look at this example. So in this example, the null assumes the average is 50. The null says mean is 50. Now I'm interested in the research that mean is greater than 50. So again, if I get a sample average that's 51, well, that's not really too far away from 50, is it? So the null could still be correct. If it's 52, still close enough. So the question is, when I say greater than 50, how large should that difference, the discrepancy, be to be judged statistically significant? Okay. So, for example, I may decide on 2 standard deviation. I'm going to say within 2 standard deviation, or actually anything less than 2 deviation, I'm going to give null mu 50 benefit of a doubt that I'm just off by sampling error. But anything above 2 deviation, I personally am just happy with 2 deviations. See, that's where alpha comes in. Anything above 2 deviation, let's say the null is not true. Again, that's just an agreement between us. Okay, so what this critical value does in effect, you can see the highlighted region is what we call the non-rejection region. The red zone is what we call the rejection region. We reject the null in this region. So remember, if the alternative says greater than, we call that a right tail test. Indeed, this is the reason we call it a right tail. It's like, what does tail have to do with this? Well, we're talking about the right tail end of the normal distribution. In this region, the red zone, we are gathering support for the alternative, and we are gathering evidence against the null. Okay. And again, that 2 deviation, I arbitrarily set that one, okay, as my cutoff point. Now, what I just mentioned here, I wrote it in a paragraph for you. Okay. So let's now talk about formally what the rejection, non-rejection region, and critical values are. Again, rejection region is the region where we reject the null, and where our test statistic actually, let me talk about this test statistic here, because it's in here. You see that test statistic? This test statistic is actually going to be a number, a value, okay, a value, and it's a value which creates a cutoff for us. Okay, that's our test statistic. It's a value that we compare against the null and then decide whether we're going to reject or not reject. That's our test statistic. So let me write that here, that our test statistic is a value that is calculated from the sample. Okay, that's what our test statistic is. And you'll see later on, it's going to end up being a formula for us. Okay, so that's what it's going to be. Now, the non-rejection region, again, is the region where if the test statistic falls in it, it leads to non-rejection. And the critical value is the cutoff point. It's the value that separates rejection from non-rejection region. Okay. And, okay, so let's move on. Let's continue on. And I have it here again for our test statistic is the value that we calculate from the sample. Okay. And that's going to help us test the hypothesis. Now, here are the 3 forms of the alternative. Remember, the alternative could be not equal to, less than, or greater than some hypothesized value of the mean. So how does the critical value come into this? In the case of a two-tail hypothesis test, the critical values, there's 2 of them. They're both tail ends of the distribution. Right and left tails. Here right, there's left. In these 2 tails, we reject the null. For a left tail test, the rejection region is on the left tail. And the critical value is right here, the value that separates the 2. In the case of a right tail test, the critical value lies on the right side. It's a positive value. Okay. And as I mentioned, in order to determine the critical value, we need to know alpha, the significance level of the test, because that's what, again, we just preset, the level of significance that directly tells us where we want the cutoff to be based on alpha. So alpha determines the critical value, and this is based on a z-test, because we're going to assume sigma is known, just like we did for confidence interval. And there you have it. So the critical value in the case of, again, of a two-tail test, this is going to be our critical value. Alpha is the size of our test, right? Significance level of the test. You divide alpha by 2, put that in this tail, alpha over 2 in the left tail. In the case of a left tail test, we put alpha in the left tail. The negative z sub alpha, that's our critical value. And in the case of right tail test, z sub alpha will be positive. Okay. And these are some typical critical values for these alpha over 2 regions, by the way, or alpha. If you're looking at 10% on the right, doesn't matter whether it's alpha over 2 or alpha. Think about just in terms of the area, how much area is there on the right side. The 10% on the right side, then the critical value is 1.28. If you want 5% on the right side, 1.645. 2.5% on the right side, 2.33. If you want this to be, for example, 0.005, then that z-score is 2.575. Now here I have an example of these. Let's take a look at these examples. So in the first example, notice that we have 5% in the left tail, 5% in the right tail, and z at that is 1.645. So our alpha here is the sum of those two, because you have one tail plus another tail. So the significance level is 10%. And this has to be a two-tail test, right? Because I have two regions, rejection regions, that is. Now, looking at these other examples below, like for example in number 940 here, we want to determine the critical values here. So the critical value in number 40 is, in number 40, this is a right tail test. So that means the rejection region, see, right tail. So rejection region is in the right side. And alpha is 0.5, so critical value is 1.645. Number 42, well, if you're doing a left tail, alpha 0.5, the cutoff is negative 1.645. And in number 44, we have a two-tail test, alpha 0.5. Remember, for two-tail tests, we divide alpha by 2. So I did, and the halved values of alpha become 0.25, 0.25, and the 0.25 I would write up here, see, 1.96. That's how I got this 1.96. So there are actually two critical values in the case of a two-tailed test of hypothesis. Okay, and I believe that's all in this segment. Again, let's take a short recess with this, and again, if you need to, please rewind and repeat the lecture, so hopefully it will help you soak the stuff up a little better. So I'm going to stop this one. In my next lecture video, we're going to look at the p-value approach. And then when we're done with p-value, we'll actually look at examples, and we'll just go to Minitab, and it's going to be really easy. It's just all of these preliminary terminologies and jargons, we need to get those out of the way. Okay, so let me stop the video now.